This is Bob Capetta from the University of Illinois at Chicago, and this is Math 121 Pre-Calculus Final Exam Review, Part 1, Problems 5 through 8. We are given the function r of x is 3x minus 6 over x squared minus 2x minus 3. We want to find the intercepts, identify the asymptotes, find holes, and sketch the graph. So our first strategy is to factor 3x minus 6 is 3 times x minus 2. X squared minus 2x minus 3 is x minus 3 times x plus 1. If something would have canceled out, we would have had a hole. Nothing cancels here, so there's no holes. In terms of asymptotes, we will have both vertical and horizontal asymptotes. Regarding the intercepts, the y-intercept is going to be when the x value is 0. So plugging in a 0 value for x, 3 times 0 minus 6 over 0 squared minus 2 times 0 minus 3. Negative 6 over negative 3, we get a value of 2. So when x is 0, y is 2. The y-intercept is 0, 2. X-intercepts, well, that's when the fraction is going to give us a 0 in the y value. So values of x that will result in r of x equaling 0. So we set the entire function equal to 0, so the numerator has to be 0. 3 times x minus 2 has to be 0. That occurs when x is 2. That's my 0 or my x-intercept. X-intercept is 2, 0. Now regarding asymptotes, that's going to tell us where the denominator is 0 for vertical asymptotes and what is the limit as x gets large for the horizontal asymptotes. So you'll notice on the bottom, if x minus 3 is 0 or x plus 1 is 0, that is going to give us a situation where the function is not defined. It doesn't divide out, so that will be vertical asymptotes. If x minus 3 is 0, x equals 3 is a vertical asymptote. X plus 1 is 0, x equals negative 1 is a vertical asymptote. No holes, again, because nothing canceled. If we had x minus 3 over x minus 3, we would have had a hole at 3, but that didn't happen here. What else do we have? Horizontal asymptotes, we're going to look at the limit as x goes to infinity. Now you may recall, if the degree of the bottom is greater than the degree of the top, we'll have a horizontal asymptote at 0. Here's a way to prove that. If we're going to take the limit as x goes to infinity of this, divide the top and bottom by x squared, of course, that's a calculus technique, and we can see that we're going to get an answer of 0. So when the numerator has a larger degree than the bottom, then the denominator will have a horizontal asymptote at y equals 0. So indeed, horizontal asymptote at y is 0. Our next move is to sketch the graph. Well, we know the y-intercept is 0, 2. X-intercept is 2, 0. Vertical asymptotes at x equals 3, x equals negative 1. Horizontal asymptote at 0. And we're going to go ahead and try to graph something that meets all those requirements. And here we go. Y-intercept 0, 2. We see that. X-intercept at 2, 0. Draw on the vertical asymptotes at x equals 3 and x equals negative 1. Horizontal asymptote at y equals 0. Test some numbers near the asymptotes to get an idea of the shape, but that's a pretty good graph given the information we have. Okay, same thing here. We want to go ahead and find the intercepts, asymptotes, holes, and then sketch the graph. So our first strategy is to factor. So x minus 4 times x plus 1 over x minus 3x plus 2. Y-intercept, plug in 0. 0 minus 4, 0 plus 1, 0 minus 3, 0 plus 2. Put all that together, negative 4 times 1, negative 4 upstairs, negative 3 times 2, negative 6 downstairs. We get a y-intercept of 2/3. Now regarding the x-intercept, we'll notice that the coefficients of the highest term are both 1, 1x squared over 1x squared. So that'll be our our horizontal asymptote. We need the x-intercept first. The x-intercept is when the fraction is 0. So setting the fraction equal to 0, the numerator is 0, so x minus 4 is 0 or x plus 1 is 0. So x is 4 or x is negative 1, which tells us then that x-intercepts will be 4, 0 and negative 1, 0. Those are both our x-intercepts. So we have the y-intercept and 2 x-intercepts. Asymptotes. Again, regarding vertical asymptotes, when is the bottom 0? The bottom is 0 when x is 3 or x is negative 2. And that did not cancel out. So again, we have no holes here. And regarding horizontal asymptotes, we look at the coefficients. The highest power is x squared, highest power is x squared. 1x squared over 1x squared, our horizontal asymptote will be at y equals 1. And just to kind of use some of the language of calculus, what happens as x gets very, very large, this function indeed is going to go to 1 because those terms are essentially not terribly important. The x squared is growing much faster. 1x squared over 1x squared, horizontal asymptote equals 1. So putting all that together, what's the graph going to look like? We have two vertical asymptotes, one horizontal asymptote. We have x-intercepts, we have y-intercepts. There's our version of the graph. You'll see the horizontal asymptote at y equals 1 drawn in blue. Vertical asymptotes as well drawn in at x equals 3 and x equals -2. And pick a couple other points if you want to get an idea of the shape of the graph. All right, next we're starting with the graph, and we want to eventually come up with an equation. First question is zeros. So where does the function cross the x-axis? Here, which looks to me like it's at -4. And here, they're telling me that that's 1, 0, and at x equals 1. So we have a 0 at -4, we have a 0 at 1. Y-intercept is also given to us. They're telling us the y-intercept is 0, 2. So the y-intercept is that. We're going to use that to find our equation. Now let's look at the asymptotes. Horizontal asymptote here. That's the first box, but that looks like it's 2. So horizontal asymptote at y equals 2. Vertical asymptotes, 2 of them. One here at -2 and one here at +2. Now can we use all that information to get an equation of the graph? Well, here's what we have. The zeros are -4, so I need x plus 4 upstairs. 0 is 1, I need x minus 1 upstairs. Vertical asymptote, x equals -2, I need x plus 2 downstairs. X equals 2, I need x minus 2 downstairs. But there's going to be some multiplier here that I'm going to be able to use. You can probably see right away what it's going to be based on the horizontal asymptote. But I'm going to use the y-intercept. 2 is f of 0 to solve for a, plugging in 0. 4 times -1 upstairs, 2 times -2 downstairs. Equals f of 0 is 2 because the y-intercept is 2. When x equals 0, y is 2. So 2 is -4a over -4, so of course a is 2. So plugging in that 2 into this function, we're going to see f of x is 2 times x plus 4, x minus 1 over x plus 2, x minus 2 is our answer there. And another in that vein, given a function, given a graph of a function, can we come up with a rule? State the zeros. Where does it cross? Here and here. Zeros at 1 and -1. Y-intercept is here. It looks like that's 0, 3/4. Asymptotes. It appears that we have an asymptote here at 2 and an asymptote at -2. X equals 2, x equals -2 vertical asymptotes. Horizontal asymptote right here at y equals 3. Let's state all those things. Again, zeros at -1 and 1. Y-intercept again at that point, 0, 3/4. Horizontal asymptote, y equals 3. Vertical asymptotes at -2 and +2. So x equals -2, x equals +2. So what are we going to do here with this? We're going to recognize that the zeros are -1 and 1, so I need x minus 1, x plus 1 upstairs. Vertical asymptotes, -2 and 2, x minus 2, x plus 2 downstairs. And again, I have to solve for a. But f of 0 is 0.75 or 3/4. So 3/4 is f of 0. Plugging in 0, 0 plus 1, 0 minus 1, over 0 plus 2, 0 minus 2. So 3/4 is a times 1 times -1, 2 times -2. So 3/4 is -a over -4. A over -4, of course, is a over 4. Multiplying both sides by 4, we get a is 3. So just substitute that 3 in for that, and we have the value of our function. F of x is 3 times x plus 1 times x minus 1 over x plus 2 times x minus 2. Next we have f of x is log base 3 of x plus 9. What can we say about this? Well, the domain, remember, you can only take a log of a positive number. So the argument x plus 9 has to be greater than 0. So if that's the case, x is greater than -9. The domain of this function will be those values of x that are greater than -9. If I want to use interval notation, round bracket from -9 to infinity. vertical asymptote, again, nothing happens to the left of -9. We'll have a vertical asymptote at x equals -9. Do some analysis with this. Let's say y equals log base 3 of x plus 9. I'm going to rewrite it that way. Log base 3 of x plus 9 is y, so 3 to the y equals x plus 9. 3 to the y minus 9 equals x. So plug in various values of y, subtract 9 and get x. So maybe y will be 0, 1, 2, -1, -2. That's what I have. Y is 0. 3 to the 0 minus 9. 1 minus 9 is -8. 3 to the 1 minus 9. 3 minus 9 is -6. 3 to the 2 minus 9. 9 minus 9 is 0. 3 to the -1 minus 9. 3 to the -1 is a third minus 9. -26 thirds. 3 to the -2 minus 9. -80 We're going to graph those points if we're going to try to graph this function. F of x is log base 3 of x plus 9. Those points again, -8, 0, -6, 1, 0, 2, -26 thirds, -1, 80, -80 ninths, -2. The x-intercept, of course, is -8, 0. That's where y is 0. The x value is -8. And the y-intercept would be 0, 2. That's where it crosses the y-axis. Okay, so there are all those points. If I were to connect them, they're going to look like that. That's our graph of log base 3 of x plus 9. Now let's find f inverse. So we're going to look at y equals log base 3 of x plus 9, and at some point we're going to have to switch x and y, but we'll do some analysis first here. So 3 to the y equals x plus 9 as we did it before, but now x and y change places. So the equation becomes 3 to the x equals y plus 9, and we want to solve for y. So y equals 3 to the x minus 9. That would be the inverse of that function. F inverse of x would be 3 to the x minus 9. Now regarding graphing it, we had these points for f of x. If you want to graph f inverse, x becomes y, y becomes x. Just switch the order. That's how we can graph f inverse of x. So there's our points, and that's what they look like when we graph those things on the coordinate plane. And there it is when it is connected. Now, in this situation, we have f of x is -2 to the x plus 3. Plugging in again various values of x, what do we get for y? -2 to the 0 plus 1, plus 3. -1 plus 3 is 2. -2 to the first plus 3, -2 plus 3 is 1. -2 to the second plus 3, -4 plus 3 is -1, etc. We can graph all those if we're interested. So this is the graph of f of x is -2 to the x plus 3. And we'll notice we have a horizontal asymptote there at y equals 3. Connecting all of them, they have that look. So there's the points for x and f of x. If I want to do f inverse of x, switch the order. If I have x f inverse of x, 0, 2 becomes 2, 0. 2, -1 becomes -1, 2. 3, -5 becomes -5, 3. And graphing all those points, that's what it looks like. Now, can we find an equation that will define that? So we have f of x is -2 to the x plus 3. Find f inverse. So y is -2 to the x plus 3. Switch x and y. X becomes y becomes x. X is -2 to the y plus 3, subtracting 3 from both sides. Multiply both sides by -1. Little tricky here. -x plus 3 is 2 to the y. Then take the natural log of both sides. Natural log of -x plus 3 is natural log 2 to the y. Y comes down front, divide by log 2, and that is our function for f inverse of x. So looking at this, then, what do we have? We had all those points before. If I actually graph natural log of -x plus 3 over log 2, what do we get? We get all those things connecting. And here we have our asymptote where? Our asymptote is vertical, and it is the line x equals 3. And that will conclude this lesson.